So now we have done few questions on relations. Let's see these questions. Okay, so now first let's see this. Get 1997 1 mark question. The number of equivalence relation on the set this is a set given containing 4 elements. What are the number of equivalence relations? Okay, so now here you have to remember something. Okay, if a set of 3 relation, the equivalence relation will contain 5 elements. If a set of 4 relations, then the equivalence relation will contain 15 elements. So this is I know this actually finding it is really tough, so it is better you remember this. In one test series I remember there were 5 relations. Actually I forgotten what was the answer. I tried finding out but I couldn't. So if I find out I will tell you. Okay, so these two I don't think more than 4 relations they will ask. So here 4 are present, so the answer will be 15, option A. Okay, so like this it's better to remember because finding it's hectic, so it's better. So there are very few things I tell you to remember, so this is one of them. Okay, so this is you have to remember. And so now let's see next question. This was asked in 1998, 1 mark question. Okay, so if you have any doubt you can always mail me. This is my mail ID, bossdeshna135@gmail.com. okay, so for any queries you can mail me here, and if you love watching my videos please do subscribe. Okay, I'm trying to make more and more videos possible now, because later may I not when college starts I don't know how much time I will get, so I'm trying to make more and more videos now. So now let's move on to next question. Get 1998 1 mark question. Suppose the A is a finite set with n elements. So there are n elements. The number of elements in the largest equivalence relation. What is the largest relation? That is n square. So n into A is coming down to as n square. Okay, so everything is present. Okay, so this when everything is present, so that has to be our equivalence relation. Okay, so here this is n square. So you can take any example like this. Let's say 1 2 3, you can find it out. 1 1 2 2 3 3, these are diagonal elements. Then 1 2 2 1 1 3, like this. Okay, you can just find it out with even an example also, but the largest will be n square. Okay, so the largest is total is everything will contain n square. In the n square will contain everything, and when everything is present you don't have to check anything, it will always be transitive. Okay, so this was 1998, and another question was 1998 1 mark question. We have already seen this kind of question, but let's practice some more so that you don't get any negative marking anywhere. So just this so much practice, it will make you perfect. Okay, so now let's see. R1 and R2 be two equivalence relations on a set. So both R1 is equivalence and R2 is equivalence. So means R is T. Okay, R is and T. Reflexive, symmetric and transitive. Equivalence is true means all these are true. Okay, so it has to be reflexive, symmetric and transitive. So now let's see. The assertions are the following assertions. R1 union R2 is an equivalence relation. R1 intersection R2 is an equivalence relation. So we have already seen transitive relations. Transitive relations are not closed under union. Okay, but it is closed under intersection. Okay, we have already seen this in previous video with example. I have told you to do the other question by your own, but since I thought of taking the question, so we have already seen this. You can take an example and find it out, but so you can see this is false. Okay, so this is not true and this is true. On assertion true is correct, as there were some example options like assertion 1 is correct, B2 is correct, both are correct, neither, like this. Okay, I don't remember, I have to see, but here the thing is transitive depend. So everything else. Okay, reflexive, symmetric, these two are closed under both this union and intersection, both ways. It is closed in both ways, but just in transitive part we have some problem. That's why it is not closed under union, and hence since it is not closed and transitive is not closed under this union, equivalence is also not closed. Okay, so this is false. R1 intersection R2 is correct. Okay. So now let's see these two questions. Okay, so this is an interesting question because they have already given you proof, and if you have to find out if the how the proof is wrong, okay, or right, anything. Let me check. Yes, it is recording. So now it was asked in GATE 1999. This is 2 marks question. So back then I think it was not MCQ, so you have to write something. So anyways, let's see the question. So and just the concept is important here. So so this is our question. Let's say Mr. X claims the following. Okay, if a relation R is both symmetric and transitive, then the relation R is reflexive. Okay, so this is we have already seen this is wrong, but he is given us a proof. So our relation is already symmetric and transitive. So symmetric is also right, transitive is also right. So for this Mr. X offers the following proof. So what is the proof here? He is giving from x related to y using symmetry. We can see that y is related to x, so x is related to y, so symmetric, since it is symmetric relation, you can say R y is related to x. Okay, so now because R is transitive also, see it is also transitive, so you can say from these two, so from these two y is common. Okay, so now we can say that. So hi, the video got stopped. Okay, so anyways, he is telling since it is symmetric, x is related to y, so y is related to x from symmetry. Okay, so from now transitive, so y and y are common, so you can say that x is related to x. Okay, so quite a good kind of explanation he is this Mr. X is giving. So here you can say all the diagonal elements are coming like this, so we can think like this is reflexive. We can think it is reflexive. Okay, so the proof is quite good explanation, but the thing is it is wrong. Okay, so why it is wrong, we have to find out why it is wrong. So it is saying that if a relation R is both symmetric and like this, so from this, okay, so if this is present, okay, so we have to see if this is present, then this would be present, then this will come. So everything is if. So this is not correct here. If a relation, so if this is present, then this will be present. So what if the relation R1, let's say this is empty set, so what, nothing is present, so it is both symmetric and transitive. It is not reflexive, because reflexive has to this diagonal elements have to be present, but this null is there, null set is there, this is already symmetric and transitive. If this present, then this will be present, then from this will come. So if nothing is present, like this, nothing is present, so this is empty set. So what we can say, this is symmetric and transitive, but it is not reflexive. So there is a flaw in this proof, that if there is nothing is present, we cannot say this is coming. Okay, so this is actually a good question. So now let's see next question here. So now let's say this question: a relation R is defined on set of integers x related to y if and only if x plus y is even. So this related to the both ways, this x and r, x and y, this has to be the addition will have to be even. This is our given condition. Which of the following is true? R is not an equivalence relation. R is an equivalence relation having one equivalence class. R is an equivalence relation having two equivalence classes, and lastly R is an equivalence relation having three equivalence classes. So now the first thing is one important thing is even can come from even plus even. Okay, again even can come from odd plus odd. So you can take any example. This odd is 3, please take 1 as 3, so this is 4. Okay, so this is coming as even. So you can imagine it like this, some examples, but this 2 classes, we can divide this in 2 classes. Okay, so even can come from even plus even can come from odd plus odd. Okay, so now we have to find out this is reflexive, this is equivalence or not. So first for that we have to find out reflexive. First let's say reflexive, we have to find out this is reflexive or not. So reflexive means all the diagonal elements. So x related to x like this. So x plus x. So this is 2x, right? So this is actually even. Anything into 2 is, this is even. Even if this x should have been, let's say x is odd and x is even. Okay, so anyways, whatever it is, if we take twice of that element, that will be even anyways. So it is reflexive. So now next is symmetric. Okay, so next is symmetric. X related to y, then y has to be related to x. This is our symmetricity is telling. If this is there, then this has to be present. Okay, and here it is already given that x plus y is even. So if we just swap this, not swap, just commutative. So addition, commutative means we have already seen x plus y is y plus x. Okay, this is over addition, it is commutative. We just change this, y plus x will always be even. Okay, for both cases, odd and even. Okay, so the both cases, so this will be even. It is given that x plus y has to be even, then if we just change the ways, y plus x will always be even. So this is symmetric. Okay, so next is transitive. We have to find out this is transitive or not. Okay, so next is transitive. So transitive means x is related to y, and if y is related to z, then x related to z has to be present. This is our basic transitive relation. So now it is given that x plus y is even. Okay, so then y plus z is also even, because this has to be present, right? This both has to be present, then we have to check this is present or not. So then x plus y plus y, I think this is visible or not, let me check. Yes, actually this is visible. Okay, so now plus z. So even plus even is basically even. So now where should I write? Here, let me write it here. Okay, so the next, so x plus 2y plus z is total is even. So now x plus z is even minus 2 of y. So even minus something, 2 of y means this is also even, because already is multiplying with 2. So that will come down to as even only, because this part is also true, even, because something is multiplied with 2, that will be even only. So this is even. So this is coming down to as x plus y is also even. So at our transitive is also true. So this is actually equivalence with 2 classes, because we are taking odd and even. So it like odd, even, let's say like even minus 2, 0, 2, 4, like this. Okay, and minus 1, 1, then 3, then 5, like this. This will continue. We will have both classes. So here it is, this option is correct. So the R is a equivalence relation having 2 equivalence classes. I hope this is actually a good question. Okay, so this kind of questions are you have to think with logic. Okay, so this is a really a good question, that's why I have taken it. So we will see more questions. So keep watching and keep practicing. Don't just see the questions, just practice. Okay, make notes and properly practice with me. So I am practicing, you also practice with me. This will make things clearer. Okay, so just practice maths in parallel with whatever subject you are preparing. Give some time for mathematics. Okay, see you in next video.